use induction.
And you cannot send your passport like this VFS or like for example here.
I think usually that to send
Because that's what we do here.
пробка в 4:30. It's right. That's logical. That's logical. What's We have 1 minute to start. If somebody has questions about yesterday, day before yesterday, ask now, and then we go. Because people come and ask questions privately, and that's a disservice to community. Because when you ask questions publicly, then other people first they understand that they aren't that stupid, that other people also don't understand this, and then the answer will be heard by everyone. Anyway, 9:30, so you will be asking questions as we go. So before we start the next episode, as in any series, I briefly recount what happened in the previous episodes. So it's all about essentially a quantity which we call S, which is minus pi log pi. And we'll be mostly using it measuring in bits, namely we take logarithm by the base 2, and it pops out in different contexts, but let me now focus on a specific context. So if I'm asking what is the probability of some sequence of symbols, and those symbols, each one can has values with j running from, and each one has a probabilities, and the sum of these probabilities is unity, then what we're saying is that the probability of this sequence in the limit n going to infinity is, because it's logarithm this, then it's 2 in the power n s of y minus, where s is this function, okay? So the number of typical sequences grows exponentially, and the entropy is the rate. I want you to start seeing entropy as the rate of growth of the number or decrease of probability, okay? So if number of typical sequences grows exponentially with this rate, then the logarithm of this number, which we defined as information, namely, we defined information as a minimal number of questions. In this case, yes, no question. Yes, no question brings one bit of information. We ask how many questions we need to specify a given sequence out of 2 to the n of s sequences. So if we take log of it, it's n s of y. So per symbol, this is your information, okay? That's essentially what we learned. But when we were doing this, we assume that those symbols are independent. That's why their probabilities were multiplying, and logarithm of their probabilities was summing, and we use the law of large numbers. But at the end of last lecture, we ask, okay, but what if they are correlated? Well, let's start from the simplest case, and that's what we did in the end of previous lecture. We defined conditional probability of some quantity j happened after quantity I. I don't remember which way I defined. So this is my condition, or how I did. No, I probably defined it. No, j of I. Let's say this way. Okay? And then we say that we now consider what is called Markov process. Namely, my state at a given position determines the probability of a next step. It could be many different possibilities. Many different letters can follow my given letter, but there is some probabilities assigned to it. And then we say that in this case, the logarithm of our probability of yn we can write as a logarithm of y1 plus sum from k to 2 to n, and the logarithm of p of j, k of, let's say, I k plus 1 under the condition of I k. Okay? So that was our definition. Now we ask how this guy would behave in the limit n going to infinity, right? We say, yeah, well, this is some number, whatever it is, but this would linearly grow with n, with a rate of growth exponentially fast, approaching the quantity, which is S, and in this case of let's call it S conditional, and this is the sum. So what you need to do is just, this is a probability distribution, right? So you just treat it, so you find that this is pi of ji logarithm of pi of ji and sum over all j's, right? And so now you say, well, but it still depends on I, on your starting position. So it's a conditional probability of a distribution of seeing j if I is given. It's conditional. Okay? So now you say, okay, but now I really want to treat this limit, and in this limit I can kind of consider it started in any position here. So I need to average also over I with the probability of I. Again, as we discussed, this is the matrix of conditional probability. This is the vector, right? And this is the rate with which it grows. Okay? You see, so in this case, it's essentially the same scheme, but instead of probability of a given number, it's a conditional probability over here. Incidentally, if we speak about language, then if our 26 letters of English were totally equally probable, then every letter would bring log 2 of 26, which is 4.7. Because there are different probabilities, it's some information about language, then every letter brings less. And then you can check that sum over pi log 2 pi's with the true probabilities of language is around 4.1. 4.11, I don't remember. This order of magnitude. Now you can say, but this is even more information about language in a sense that what we discussed, this vector follows from this matrix, but not other way around. Conditional probability include information about probability of a given letters in a long text, but not other way around. So you may ask how much this would lower your entropy, right? And of course, you need not stop here, and Shannon, indeed, who did all this stuff, checked what happens when you're given 2 letters and ask what is the third letter. It lower entropy a little bit, but this is the main step. And then you find out eventually that your S of English language is of order 1.4. Shannon was so thorough that he did it other way around, and he actually took people, normal, high school educated people, not overeducated like you, and asked them to guess the next letters in the text. But you can also do it other way around, just take your text and eliminate part of the letters and see how it's comprehensive. It's, in a sense, my favorite example of this. It's a true poster, and you can Google it. It's actually part of some pretty famous poem. It was in New York City sometime in the 70s. Could you read it? That was just in a New York subway. It was a real advertisement. namely people who could read it, came and could get what? If can read this, you can, we already read it, get, I was good, you can find a good job with high pay. So people who were able to read it, apparently at least high school educated people. What was the job, incidentally? Could you guess? A secretary. 50 years ago, secretary was very well paid job. This was all before these computers, editors, etc. So you really need to listen and put it into it. So it tells us the same thing, which we already seen in the genetic code. You remember in genetic code we had 4 bases, triplet code, 64 possible combination, and only 20 amino acid. So genetic code is triple redundant. Almost any mature language, I mean Hindu, Hebrew, English, Russian, approximately triple redundant. Usually the older the language, kind of the more redundancy. Okay? So, and this is actually triple means that this relatively to this. Okay? So this is the entropy of an uncorrelated set of 26 letters. And this is the entropy of any real text written by these 26 letters. Okay? Of course, you can guess people speculate why would we need triple redundancy. And the evident idea, of course, is that you need error protection. Right? Which means that in this text, you can write it and some letters could be just, come garbled through the now in texting, of course, in 21st century, we start using it really with gusto, right? So this is what we're exploiting, triple redundancy of a language. But it could be there is more about it. There is something which tells us how our brain works. And a little bit later today, I'll tell you about Bayesian framework and what is updating your prior belief, etc. Our brain likes confirmation. And Lewis Carroll, who not only wrote Alice in the Wonderland, but also Hunting of the Snark, there is a sentence which repeats over and over, what I tell you 3 times is true. And this apparently seems like how our brain works. It needs reinforcement, and triple reinforcement is usually enough. Last thing that I want to talk about this thing, then why we're using alphabet if it's so redundant? I mean, if this is a true entropy, we can re-encode it, not in letters, but in something, in bits, etc., using variable length code, so that the mean information per new symbols will be this, and that will shrink it 3 times. Okay? Alphabet is one of most strange invention of mankind. It was done only once. All alphabets are just a result of modification of original Semitic alphabet. All previous system of writing were logographic, which is very natural because we don't convey message in letters. We convey information in words. Word is a unit of meaning. So all system of writing, and there were many invented independently and separately. Chinese, Egyptians, I mean, people in Mesoamerica, all invented their own logographic system, which means that the graph is a meaning. Every picture is a word. Then how many actually pictures you need to know if you're an educated person? Well, you ask any Chinese now who actually know it, right? They learned it. And they say, well, at least a couple of thousand if you're an educated person, but generally more. Well, a few hundred would not do, right? That's how many things, which means that your writing is a very elite profession. Only a small part of society can do this thing. right? And there are people, scribes, who can write, and people who can read, priests. And then sometime around a little bit over 3,000 years ago, apparently not very educated people. Now the oldest thing is, again, all the first alphabets, they are Semitic, but the oldest things are found in Egypt. They found this new strange thing of writing, which is phonograms, not logograms. Think about it. They try to write in unbelievably crude and imperfect way the speech sounds. Okay? There are many speculations who were those people. There's bands of soldiers for hire, or some, I don't know, Semitic people living in Egypt and they needed their own code. But it eventually came down to the fact that how many different phonemes we use. Phoneme is an acoustic unit which changes meaning, right? And it was found, well, there's still linguists argue about it, tens, 30, 40, 20, 30, 40. So you need that many letters as you have phonemes. Anyone can learn 26 symbols. That's not 3,000 symbols, right? It was a huge immediate democratization of all this process. And the book that yesterday I've shown you this text, the beginning of the Bible. This is the text written on this alphabet, okay? And it was something which was meant to be read, well, at least by all males of the tribe, okay? It was really great invention and was never repeated. It was Aleph, Bet, Gimel, Alpha, Beta, Gamma, Greek alphabet, Latin alphabet, A, B. It's say all follow from the same alphabet. So this invention was made only once. So I'm just trying to show you how encoding is a really very important part of our civilization. What's another great encoding? Numbers. How you encode numbers? Well, you can say, well, this is 1, this is 2, this is 3. Well, when you come to really big numbers, it would be really long texts, right? So again, you try to use this idea of subdivision, right? So you start to use, and this was now invented by a Persian, Al-Khwarizmi, you start to use a positional system. So you write this, and now the meaning of it depends on its position. And it's also algorithmic, which name follows from the name of Al-Khwarizmi. Khwarizm is a city, right? So it's 2 times 1,000 plus 2 times, plus 0 times 100, and plus 4. This is an algorithm, okay? So this is another great invention, not that monumental as an invention of alphabet, which introduced into the encoding algorithmic, namely what operations you need to do depending on how you read your code. This is a code, right? So, and of course, then you get to genetic code, and then you realize, and it's essentially the message which I would not be able to give you in 5 lectures, but if you read a book, you understand that practically everything we do inside this engineering is looking for a right encoding. Building a theory means a most compact encoding of the data. Okay? Good. Yes? This same sequence, but now I know that in this sequence, letters are correlated in a sense that there is a probability of letter J following letter I. But the question is the same. What is the logarithm of probability of a very long sequence?
So why is it independent of the sequence? Because S is summed over all possible sequences. So why is the
S is something which comes of this probability. S is defined with this probability. It's Pji log Pji.
But you're summing it over all.
And then I also average over I, which means of all possible first letters.
Yeah, so log, also but you said log of P goes to n of S, n times S.
Yes.
But this S is independent of sequence.
Yeah, it's minus, incidentally. This S is independent on sequences just the same way as it was independent here. That what was I formulated, almost all events are almost equally probable. So this is a probability of a typical sequence. Typical sequence. But what we know from a law of large number, then when n goes to infinity, atypical sequences are exponentially rare. Okay? It's exponentially fast approaching this value. Okay? By typical, I means that if you look at this sequence and you count in this sequence how many times B followed A, it would be something which don't change with n. It's already saturated to its asymptotic value. That's the definition of typical. That's the and also frequencies PIs. You know, these PIs, frequencies of every letter, conditional probability of every letter following the letter in this sequence is the same as is in your ensemble. That means typical. There are atypical sequences. But as n goes to infinity, there are fewer and fewer of them. Okay? More questions? Okay. And now we take this magic tool and we use it in a totally new setting, which shows you how actually powerful and general is the tool of conditional probability. Okay? So now what we do, we start treating everything as a message. So let's say you are experimentalist. So there is something which we call B is what you try to measure. A position of impurity in a given lattice. It's something which has a 10 to 23 possible positions. And what you get, it's called channel. You get A. Is a reading on your device. It could be, I don't know, a needle which can have like 20 positions. Okay? So now you want to know that, okay, you know this, right? Now, if you know this, it tells you something about this, but not one-to-one. So in most general setting, you characterize it that this B, you ask if I get a value of A, which is AI, what is the probability of having Bj? This is the same conditional probability as we discussed over there. It's now sum over J, which is unity. So some value of A it has. Okay? Now, the same way, you may try to use the same setting as to define the respective probability. And let me make sure that I'm using right notation. So you can define now S of B under condition of A, which would be a sum over all J log P of B J A I log P of B J A I. That's your conditional probability. Then you need to take it with the probability of AI and sum over I. That's exactly like we did for the text. So if we had a text over here where we have this I plus 1, all the symbols, y plus 1, then this would be information which a given sequence gives you. But now we look at it different. Namely, we don't have B. We only have A. If we were given pairs A and B's, that would be like in this text. But now we ask the question, how much measuring A it gives you information about B? How much? It's not this, right? Because now B's aren't given. So we ask, what is the information of B given A by measurement of A? For this, we need to understand how much uncertainty is lowered after we learned A. This is how much uncertainty remains. After we measure A, there is a probability distribution, and it is its entropy. So it's a measure of uncertainty about B when A is measured. So what is the information that we obtain measuring A? Huh? 1, why 1? What was original uncertainty before we started measuring? Entropy of B, of course. So what we need to say that this must be entropy of B minus entropy of B under A. And that's the real magic tool, and it's called mutual information, and relative entropy is its slight generalization. Okay? So now, apparently, it's just uncertainty that was before, that uncertainty which remains after measurement. Okay? Now it's so important that we now write it in many different forms. And for this, we'll use what is called, and which also will be using over and over, it's called chain rule. I'm sure you've seen it, but if not, then it's a very simple thing. So if I would have independent events, and I'm interested in the probability of A, I, and B, J, this is a joint probability. How it's probable that A takes the value J, I, and B takes the value J. If they would be independent, that would be P of AI and P of Bj, independent. But they are dependent. And this dependence is expressed in terms of a probability of Bj under AI. Now, if I multiply it by the probability of AI, I would obtain the probability of AI and Bj. Usually, people write it Hebrew way, from right to left. And then let me rewrite it so that it will be. So first you say, what is the probability of having AI? And then what is the probability of having Bj given this AI? Right? It's called a chain rule. And it's essentially the most important instrument of it, because now you can rewrite this formula. You can realize that what is standing here is P of AI Bj, right? This times this by the chain rule is just the adjoint probabilities. And now, if you write this formula, what you realized it is, this is sum over J P of Bj log Bj, P, well, sorry, log P of Bj. That's my entropy of B. That's my entropy of A minus this quantity, it's P of A I B J logarithm P of B J under condition of AI. Now, of course, here nothing prevents me from summing over A and adding AA, right? The sum over I would just be unity, right? So now I have the same quantity here, so I can put this log right over there, right? So let's do it. You remember there was a log of P of Bj, right? Now, this you can write again, this quantity as P of AI Bj divided P of AI by chain rules, right? Any conditional probability is a joint probability divided by the probability of your condition by chain rule. Now you understand amazing thing, that it's actually symmetric. Conditional probability is asymmetric. Mutual information, and this quantity is called mutual information, is symmetric. Okay? This is symmetric, this is symmetric. Moreover, P log PAB it's with a, well, with the sign, this would be minus S of AB. And now PAB log B is the entropy of B. P log PA is an entropy of A. That explicitly shows you that it's symmetric. And also give you an important statement first of all, symmetry, I really want you to appreciate that A and B are very different things. This could be something like 10 to 23 position of your atom. This could be like 10 readings of your thing. So all these probabilities, the probability of B lives in a huge space, probability of A live in a small space. Entropy of B is huge. Entropy of A could be small. Does not matter. Their degree of correlation, of course, is symmetric thing, which tells you that if you are given a reading of your device, you learn about the position of the atom as much as if you are given a position of the atom in this huge lattice, tells you what would be the reading of your device. Okay? It's something which is, it's trivial and it's important. It's really important to appreciate. And people often make a picture, and I also like this picture, even though mathematicians usually frown about such picture, say, well, that's a physicist way to... I had a friend who is a great mathematical physicist, and he had this saying, he says, that your way of making your discoveries in physics is misinterpreting my mathematical statements. And this is a very fruitful way to do physics. When you misinterpret what mathematicians say, just try that it kind of belongs wider. So let's draw it. It's called Venn diagram. So let me call it this S of A, okay? And now this would be S of B, okay? Where other things would be on this on this diagram. Okay? So if I would just draw okay, just to make it right, this would be my S of A under condition of B. This would be my S of B under condition of A. And this would be my I of A, B. Okay? So again, this is S of B minus S of B under condition of A. That was our initial idea. How much information about B you get measuring A? Initial uncertainty minus final uncertainty. But it's the same if you take S of A minus S of A under condition of B. Okay? I want you to meditate half a minute just looking at these two formulas and in this picture which represents them. You learn, I mean, how many of you knew before what is mutual information? %. Okay, good. Then that's your happy day, guys. The remaining 90%. It's your happy days. You now got one of the most important tools in the modern. Well, your future self-driving car will be all working on this quantity. Okay. So now, first of all, yes, question.
I'm confused about the initial statement that you made before this discussion you started about the English language alphabet. If you assume it to be completely like random, like if all the letters were appearing equally likely, then you had the average code length that you needed was basically 4.7, right? Is that okay?
I don't know, you asking question or you making a statement?
Okay, so let me complete. So, and then you said
Maybe we can give a mic because I want everyone to. Do you have a microphone? No? So while we are bringing microphone, the statement was that if you don't know anything about your alphabet, then a message brings you logarithm 2 of 26 per letter. That if you're totally ignorant person, you never seen English letters, you just look at a long list and you just count how many different letters, 26. So that's your information. Now what's your question?
yeah, so then you said like if you assume that like if you only look at the correlations between the two letters, then you said like the average code length that you require is around 4.1, right? And then I think what you said later was that if you allow your preceding letters to have like longer length, like
Yeah, I
L
said
letters, L minus 1 letters have
Yeah.
sort of appeared, and then basically you ask what is the likelihood that I will get the next letter. In that case, you are saying that the code length that you require is only 1.4, which seems very weird because like even though like an English alphabet or any language as such would have like can have infinite number of almost
I've shown you an
words, right?
example. This is an example in which 2/3 were eliminated. If it looks weird, I mean,
Yeah,
get
but
used,
this
get
means
used
that
to
I
it.
can. This means that I can probably write down like let's say works of Shakespeare with just a few, only at 2 average length of let's
Look,
say.
all of your people do it every day by texting. You just emit letters. This is what you do. And on the other end, your person understands perfectly what you mean. Okay? So if you find it weird, okay, that's the world you live in, right? We have triple, approximately triple, a little bit less depending on the language. Okay? So again, what I'm saying, if you never seen, I don't know, Sanskrit, you just get a sequence of letters, then how much information you get? It's a logarithm just of a possible number of symbols. If you know the language, then it's triple redundant. You give triple less information because a lot of information you already have. Every prior information reduces the information of the message. So you may record it and compress. Okay? That's the message. I mean, texting is just, when I was started lecturing on this 20-something years ago, there was no texting. Okay? And the people were really kind of surprised about this redundancy of alphabet. Now, like everybody knows, of course it's redundant. We just use it every day. Okay. Back to mutual information. Questions?
Is conditional probability also symmetric?
Huh?
Conditional entropy.
Yes. So what's the question?
Is conditional entropy also symmetric?
Also what?
Symmetric.
No. No, of course not. Conditional entropy is not symmetric. But mutual information is symmetric. Again, you see, this could be huge and this could be small. So this must be also huge because this difference is equal to this difference, right? Clearly, if these aren't equal, and they aren't necessarily equal, they live in different spaces, right? B can have 10 to 23 values and A can have 10 values. So they're apparently very different. So of course, these are also very different, okay? But their difference is what matters. The degree correlation is mutual. And now, what particularly as I'm talking to physicists, when you were talking about correlations and you got your undergraduate courses, the usually correlation was something like A times B. It's always some pair correlation, okay? Or A at time t times A at time t plus tau, okay? So, and mentally, and this was totally inappropriate for 21st century people because it was all built more or less on 19th century physics and statistics where we mostly worked with Gaussian processes. And I won't go, I don't have time to give you separate lecture on Gaussian random processes and Gaussian channel and all this stuff, but it's important to know that Gaussian is a distribution which is completely determined by its mean value and by its second moment. If you have a multidimensional space, again, Gaussian distribution is determined by the matrix of a pair correlation. Then for Gaussian process, wait, I have not finished. Then for Gaussian process, you can characterize the degree of correlation by pair correlation. For any other statistics, this is the right measure of correlation, okay? And now this message is very simple and it's extremely powerful. And now, because I'm talking to you as a researcher to researcher, I recently had doctors from a hospital came to me and telling us, they are treating bipolar disorder. It's, it's a very, it's a disease and they usually treat it by lithium and it's a kind of poison. So they really want to know if a person would be responsible or not. So they were studying neurons in the lab, taken from stem cells, etc., getting some signal. And we know that they are correlated, but we need a proper degree of correlation because the statistics was as non-Gaussian as you can imagine of these things. And then what we just published in the journal Bipolar Disorder article, which shows that you can improve like 40% your prediction using this quantity, right? So what I'm saying is that entropy is a right measure of uncertainty. You can use different measures of uncertainty. And Prabha told you, for example, that you can use 1 minus trace of p squared. It's quadratic measure of uncertainty, right? There are different things which are sign definite, which are 0 when you're totally certain and when reach some maximum, etc. But something which is really universal and has all the properties of convexity, which is very important, is a logarithm. And mutual information is something which is built on a logarithmic definition of entropy. Okay? Questions? Yes. Take a mic.
Yeah. So again, I'm sort of hung up on that same question. So just a follow up on that. It's like So what is the mutual, this not mutual information, but the entropy for, let's say, DNA sequence? Typically, do you know what is the?
Good question. No, I don't know. That's definitely
Because
written.
from what I
written,
heard,
written somewhere. Well, you have 4 letters, 4 bases, A, B, C, T. And generally you can say, okay, and you have a triplet code, right? So you actually, your units are triplets. So you can naively say that it would be just a logarithm if they would be equally probable. They aren't equally probable, and they are highly correlated. That's a good question. I don't know the answer. Look at it. Look it up.
yeah. So from somewhere I basically heard this, that DNA sequence typically has much higher entropy than, let's say, a language, like English, for an example. And if you look at like a computer code, it's a bit more structured, so it has a higher this entropy.
We can
but
compare them easily. Just make a binary encoding on one, make a binary encoding of another, and compare this sequence of zeros and ones and this sequence of zeros and ones. I don't know which entropy is larger, and
in other words, like
the
it's a
entropy,
bit more
yeah.
like this like computer language is. I mean, it's like the words and the codes are a bit more like predictable in some sense, right?
Again, I don't know, but in some sense that as far as we're talking about
The main question that I have, that the reason it doesn't sit right with me, because
what does not seem right?
For
Okay,
example,
ask
like the
question.
English, yeah. So English language, like if you look at the long range correlations among the letters, you're saying like that the overall entropy is only like 1.4. It's less than a 2-bit. That's what actually is a bit. I know it comes from an average, basically.
It's not a question, it's a statement. You said, I
It's a
find it
statement, but
strange.
it's a bit-
So you find it strange. Okay, we've heard that you find it
So
strange.
essentially, you're saying that
Like Feynman said, it's not a question, it's a statement. You find it strange, it is a true fact. So get used to it.
no.
Okay?
So my question is then.
Then ask questions.
Yeah. So my question is like, so when you talked about like this ATGS and the coding part, right? You said that if they were equally likely, you would require 2-bit. And then we talked about this Hoffman encoding, in which we kind of were able to shorten the length of certain codes.
Ask question. You're telling me what I told. Yes, I told this. Ask question.
So suppose if we were to look at the lecture recording of this today's lecture, can we reduce? Can we just use like
Yes, if this is a question.
Yeah.
Can you take a transcript of
Yeah.
my speech and record it 3 times shorter? Yes, that's the meaning of triple redundancy of alphabet. Exactly, that's the meaning. So if this is your question, this is the answer. Yes, you can take any text and encode it 3 times shorter. Okay? So now let me go on with the lecture. If you find it strange, it is, but that's the fact. Yes.
So this correlation between the earlier way of defining correlation which you do for Gaussian variables, let's say 2-point correlation, and this mutual entropy is you said another way of defining correlation.
Yeah.
But now suppose you have a finite data set, so this one probably requires a larger data set to compute, right? Because you need to find the probabilities from the given data set.
Yeah, of course. But truly, nobody really knows any entropy of anything of remotely of interest. For example, I'm a turbulence theoretician. I do fluid mechanics, okay? So you say, okay, here is my turbulent flow. What is the entropy of it? What the hell? I need to compute velocity at every point. Well, at least in 10 points. So if you try to think about this formula, where is this? SP log P, okay? This P and this I could be a vector, right? So it could be, so what we really know is maximum 4-dimensional distribution. In a space already of 5 dimensions, you need so many bins to create a meaningful distribution that modern computers don't work. But then we have a very smart ways to estimate entropy, and this is a very interesting modern part of information theory. For a key word is Lemperl-Ziv algorithm, but there are many others. So you get a stream of data which come out of your some kind of multidimensional. And so you try to record this stream of data in a most compact way. It's like a running procedure. You get a longer stream of data, you look back and you kind of change your code a little bit. And now you try to see whether this rate of encoding kind of saturates somewhere. Then you try to guess, okay, that's my entropy, because this would be an asymptotically way of encoding, right? But it's, I mean, computing entropy of anything interesting, it's really, that's what most people do most of the time. Questions? Yes?
So this I, B, comma A is the information of B if we have A.
What is given is at the right? Yeah, condition is on the right.
Is it a kind of
This is under the condition of I, this is the probability of B.
so is it a kind of conditional information and we are calling it mutual information? So there is it
Mutual information is the information that you get about B measuring A. And when I'm saying measuring, it's a very, very general setting. You have a memory, you retrieve a memory. You can say that this is a message sent in time. You recorded it back then, now you get it. Okay? Measurements, communications, everything could be treated as communication. But the point is that the mutual information is symmetric, yes.
there is no quantity like this conditional information. It's same.
Conditional entropy is this quantity. How much uncertainty remains about B when you measured A?
Yeah, this is conditional entropy. And is there anything like conditional information also? No?
You're welcome to, to introduce. No, information is information about this. Mutual information is a degree of correlation. That's why it's called mutual, right? But essentially, you know, entropy is a degree of uncertainty. If you completely eliminated uncertainty, that much information you got. That was your entropy. Okay? Now, information of how much A carries about B is an uncertainty which was before minus uncertainty which remains after. Okay? Yes? Questions? Wait, there was the girl. Yeah, no, yeah.
I just wanted to make a comment about the conditional mutual information. So if one had a tripartite system,
Oh, yeah, of course.
one could think about also conditional mutual information.
You can make A between A and B, which is symmetric, conditional on C. And of course, you can go next step and next step. And then you realize that actually you can do a more sophisticated combinations. And this is called interaction information, which tells you how much correlation between three quantities, which is not present in any pair of them. I won't go there. It's what people who do usually topological phase transition and other things, who try to really kind of get rid of all the correlation except something which lives in the whole system. There are many ways to play this game. These are entropy and mutual information are two examples of an infinite hierarchy of measures. Okay? And if you look into the book, then you can find a general formula, which relatively recently was invented, which tells you how to build this hierarchy in many steps. Okay? Good. I like that you ask questions because it shows that we're doing. Okay. Any more questions? Good. Take a deep breath. Close your eyes. Relax for 2 minutes, and we'll go forward. So now what we'll do, we'll again take the same, from now on we're playing with conditional probabilities conditional entropies, and I'll show you some other thing which is very, very useful, and it's just a chain rule, but a very particular form of it. So now, let me just scroll down. What I'll do it's called bias framework or bias formula. And believe it or not, I'm so old that when I grew up, nobody taught us this. It's just unbelievable. Because this is one of the most important tools, at least of experimentalists, but of a good theoretician as well. So now you just let me write a very, take A and B, very specific quantities. So it would be E and H. This would be my evidence or data. You can think about A. So A is what obtained is my, but H would be a hypothesis. Hypothesis being true. Okay? So you can ask what is the probability of giving this data and my hypothesis being true. Okay. Well, by chain rule, you can write it in two ways. It's a probability of my hypothesis times probability of my data given this hypothesis. Right? Good. But you can also use a chain rule and write it in the other way. So this is the probability of getting my data times probability of this hypothesis being true given my data. Okay? Now, what is the year? 1763. I just want you to appreciate. And again, that's the people who invented logarithm. You start to do a lot of computation and you start to estimating probabilities because it was the first social system. You need to pay pensions to people. You know, the British were pretty advanced people at the time, and they started to ask, and then Germans started to ask questions, what is the probability that a given person will live that many years, how much money then I would need to pay him a pension? All these formulas that we are writing, they actually came out of here. And so I say, now let me write it as the following form. The probability of my hypothesis being true given the data, this guy, it's equal to the probability of my hypothesis being true without any data. It's called prior. Times P of E H divided by P of E. And this is called bias formula. And it tells you how you update your prior into posterior probability using the data. Okay? So you do, you measure, you get E. And then you ask, what is the probability of this E given my hypothesis divided by probability of E in all cases? My hypothesis being true or not true, just in all cases. Okay? Without any exaggeration, one can say that what is called reproducibility crisis in all the sciences from psychology to social sciences and unfortunately partly in physics too is that people don't use this formula. Okay? Or misuse it, or abuse it, or whatever. And of course, the most famous abuses are conspiracy theories. Okay? Let's say your hypothesis is that COVID epidemics is a proof of a huge intergovernment conspiracy. So your evidence is epidemics, and your hypothesis is that Chinese, Americans, and European governments all conspired to create this, hugely increasing their power in the process. Okay? So now, in this case, you say that what if this hypothesis is true, namely there is a conspiracy? What is the probability that they would choose pandemics as a tool? Pretty high. if indeed they was this at this point, conspiracy theories stop thinking, right? And they consider, and this is typical mistake, because then you ask what would be the probability of epidemics happening anyway without any conspiracy, and what was the prior, before COVID happened, how many actually people were thinking about this huge conspiracy. Because, this government from time to time go to war with each other. Apparently, they aren't that much in conspiracy. Right? So this is a kind of funny example, but also it shows you how actually it works when you do tests. And this is another good example of bias formula. Let's imagine that we have now two things. We have H1 and H2, and they are mutually exclusive. Okay? So the probability of H1 is 1 minus probability of H2 overall. So they're totally mutually exclusive. And now you may ask, okay, so what is the probability of H1 being true given evidence? It is the probability of H1 without any evidence, probability of E given H1, and now it's this P of E consists of two parts. Probability of H1, P of E H1, it's the same as here, but it has another thing, a probability of H2, P of E of H2. Oh, first of all, if you're experimentalist, or a theoretician trying to think about Gedanken experiment or whatever, and you have some hypothesis which is originally is very improbable, then this is a small number, right? So trying to devise an experiment which would measure this is not very relevant, because this is a small part of it, of your denominator. So it's much better to try to disprove the opposite hypothesis, which has a higher probability. But now let's see how it works, namely that the fact that your prior could be small are testing the probability of your result. Let's say you do a test. So H1, you're a drug user. H2, you aren't. Okay? And so you do a test. And you say that this test is 99% sensitive, namely, if you're a drug user, in 99% you would get E. E is positive result. Okay? Or you do a COVID test if you don't like this drug connotation. And it's also 99% what is called specific. Namely, if you aren't a drug user, only in 1% of the cases you can get by mistake a positive test. Okay? Which means that you know what are those probability. This is 0.99, and this is 1 minus 0.99, right? So this is your probabilities. Now, what you need to know is this one. So this is about test. So you go, you do this COVID test, or drug test, or police stop you and want to check a level of alcohol in your breath. And then you ask how reliable is this test, namely what is the probability that given a positive test, I am COVID infected. Well, it depends on this, right? So now, that's why at the beginning of any pandemics or in a clean, almost drug-free city, let's just take this, let's say 0.5%, okay? Then you plug here this number. Just let me give you the result. I computed it somewhere. So this you take this, multiply by 0.99. So this is large, but this is small. This is small, but this is large. It's closest to unity. and you get 0.33. You see, so this bias formula, despite its triviality, it's really a very nice quantitative tool which tells you how much is really your data support your hypothesis, okay, and how much you can trust the test. And another thing I want you to notice here is that it's a change of meaning of probability. And it's not recent, it's 1763. It's just at some point we were so kind of overwhelmed by the beautiful French continental mathematics who treat probability as something as repeated events. We were always learning probability throwing a coin, right? Which assumed that you have many identical events, and we were asking about the frequency, what out of these identical attempts, which outcome comes this or that way. And then Kolmogorov built a beautiful axiomatic theory which uses this ensemble, so you have this algebras, etc. You pick and you choose, but you can pick from other places, but they are confidential spaces. This is a totally different framework. There are no repeating events here. This is an expectation. Of course, later this word expectation, that's what we used to define mean value. It's about what happens in your brain, like what you expect. And that's what you now need to expect. Okay?
So, in this expression, PH1 basically is like the police who is thinking that I have taken drugs. So PH1 is that, right?
H1 means that you are a drug user.
So PH1 is
so
the...
you have positive test, and
Yes.
H1 is that you are a drug user.
Yes.
The probability that you are a drug user with a positive test,
Yes.
in this case, when there is almost clean city, you know, why it's so mentally difficult for us to believe this result? We don't like to think about ourselves as just one out of a huge statistics. So you think, well, okay, my test is positive, I must have COVID. Well, with that probability, if it's the beginning of pandemics, where only few people. Okay? Mm-hmm. More questions? Yes?
Sorry, am I audible? Yeah. I was wondering, how do you compute P of H1 in a city? I mean, how do you compute P of H1?
P of H1 is usually you go to police and they would take you, for COVID, let's say. For COVID, you usually know how much people are infected on average because you do, for example, you go to school, you do sweeping test and you see what percentage of population comes out infected. But if you don't know it, there is no way you can estimate probability or reliability. This is called reliability. You cannot estimate reliability of any test if you don't know prior.
Yeah, so in that sense, to know P of H1, we need to know the evidence has to be, if you, let's say you want to measure P of H1 and you did tests, we don't know whether we can rely on that test, right? So it's a...
No, there is no circle here because when you do many tests, you know that they are 99% reliable, which means that you get this quantity with a 1% reliability. That's okay. So you get this one with 1% of it error. That's always, any measurable number had an error bar. So the fact that you have your test, which is not completely reliable, is just because it's 99% sensitive. So okay, so this quantity you know with an accuracy of 1%. We can live with this, okay? But 1% of its value, okay? More questions? Yes?
Do we need a perfect reference test to perfect reference test to actually make this?
Perfect? What do you mean perfect?
Because if Perfect reference test means because to know pH1, we need to know that my first reference test should be actually one-to-one correspondence with the hypothesis being true,
Yeah.
isn't it?
That, in a sense, tells you that you can't say anything if you're just starting. And this framework is something which is really orients you from looking at probabilities as something which is given, God-given from some ensembles, but something which you, part of a dynamical process that you do step by step every time, multiplier by this factor. Okay? Look at global warming debate from this viewpoint. We don't have ensemble of Earths which we can run with different, initial condition. So when people say, with a probability 85%, the temperature would grow by 2 degrees by this, what do they mean probability? They mean expectation in this very sense. Okay? And how they mean it? They start from something which is very unreliable. They do data. They check which way your probability changes. If it increases, then you say, this is my rate of increasing. And you only trust many, many, many data which change your way. Because you don't have ensemble of planets which you can compare results of different evolutions. So that's why this Bayesian framework is now much, much more popular and practical than a standard gambler's approach where you throw a coin and you assume that it's a perfect coin, like every time it's kind of, okay?
So,
Yes?
so the prior that the police would use, that depends on their experience in the city, is that right?
Yes, and it's always updated.
It's always-
Always updated. For example, for doctors during COVID epidemics, you start from it, but at some point it will be 20%. And then test will be very reliable. The moment this is 0.2, this is 0.9. You see? Because it's directly proportional here, and now this will be a large number, which means that this would be relevant. So this is the point, that the tests are unreliable at the beginning of pandemics. And my wife, she works in pharmacology, and I actually learned it from her. It's good to teach each other. We were trying to have a daughter after 2 sons, so we were studying biology and statistics together, and she actually taught me this. I said, how the hell is the same test? How the test could work better later in the pandemics? It's the same test. And she said, well, because it's small. The probability of it being true multiplied by this. And I remember myself being surprised about it. So it's kind of, but then again, I'm an old person and nobody taught me this at the university, and this was a totally, this was a crime against education. Okay, how we're doing? Yeah, I have one more thing to tell you today, so let me go about it. So now what I want to discuss, the last thing today, is how you actually do this thing, test after test after test, and how fast you disprove or prove your hypothesis. Okay? So again, now I would like to discuss the rate with which you change this factor, which, for example, tells you that your hypothesis is not true. What you expect it to be. Again, if you are theoreticians, never try to solve any problem or do any computation without first guessing the answer. Never, ever. Because when you guess, even when you wrongly guess the answer, a bad plan is better than no plan. So what do you expect it to be? The rate. Entropy is always the rate. Rate is always the entropy. The question is which entropy. Let's look into it. So now, I ask a very simple technical question. So, you make a hypothesis of a very particular type. Namely, you assume that your probabilities are QIs. And again, I runs from 1 to n. So this is your hypothesis. Okay? The point is, the true probability is PIs. It's like in this asymptotic equipartition, this long sequence. So you look at this sequence, you assume that it's typical, you count how many times happen this value and happens this value, and you assume that this is a true probability. But it's not. So now you'll be looking forward, continuing your sequence, getting new and new and new data, and you want to estimate how fast your probability of your hypothesis being true would decrease with n. Okay? So that's a formal question that we ask. Okay? Let me get to it to write notations. So, okay. So now I ask that if my result I, you observe it how many times in a very long sequence? That's a true probability of I. So how many times you will observe it in a long sequence? Pi times n. Okay? So that what would you, but your hypothesis, which you initially accepted, was that the probability of this is Qi, and every event is independent, so it's a power in the power Pn of n. Let me write it as an exponent Pan logarithm. Just for the sake of it, I would write exponents because I will be using Stirling in a standard way. Qi's, okay? But now, again, it's not a probability. It's just a product of probability. You now need to multiply by the total number of possible combinations in which you, wait, where is it? Yeah, here. So now your probability would be exponent Pi n logarithm Qi's times the number of possible sequences that you can have P1n factorial, P2n factorial, Pn n factorial. Okay? As usual. So this is your judgment, Q in the Pn, and this is a possible number of such combinations. So surely you get it's in the limit of n goes to infinity. So you can write this guy as exponent of a logarithm of it. Well, we already know what is it. P1n, Pnn factorial. You use Stirling formula, that would give you n log n, that would give n log n. And as a result, you obtain this probability as an exponent n log q, p, well, it's sum over I, n log n, that what comes from this, plus Pi log Qi minus log Pin. This is all these guys would be here, and this would be a sum over I. So now you see that n log n would, this log n would cancel this log n, and what you get as a result is exponent minus n. As we expect, the probability exponentially decreases because P is not Q. Must be, right? And so what stands here is what you already seen in Prabha's lectures is Pi logarithm Pi Qi. And this magic quantity is called relative entropy. It's also very easily memorizable because it's P log P over Q. Again, it's 0 only when at every I, Pi equal to Qi. Okay? Now, it's pretty easy to see that it's always non-negative. It's called D. And it's called D of PQ. Sometimes purists put here two lines to distinguish, to stress that it's not a conditional. It's not a conditional entropy. It's a relative entropy between P and Q, and it's not differences of entropy. Now, if you use a simple formula, that logarithm x less or equals than x minus 1, then it's pretty easy to show that if you take minus d of p over q, and this is the sum of pi log p over q i's, and if you say that my log is less than x minus 1, so you say that this is now less or equal pi over qi minus 1, right? And wait, what I'm doing? Yeah, qi over pi. Sorry, I took minus d. So it was qi over pi, and this was minus. Okay, so this is a sum over qi's minus sum over pi's. They are both equal to unity, so this is 0. So it tells you that minus d is less or equal than 0, that minus d is non-positive, which means that d is non-negative. So d is positive. The friend of mine who I mentioned in the first lecture, who always thinks about entropies as a degree of surprise, he has a very nice way. He actually taught me, as Anton Kapustin from Caltech, he is a kind of quantum theoretician. He tells me very nice way to, he says that the very fact that relative entropy is non-negative and it is asymmetric. It's not symmetric with respect to P and Q. That's why it's not a distance in any geometric sense. It's not a matrix. Distance always is that, I mean, look, think about it as a degree of surprise. If I believe that the distribution, and I always have true beliefs, right? So my belief that the distribution is pi, then my average degree of surprise is, of course, the sum of pi log pi, right? This is my average degree of surprise. But now I see a person who believes, for some strange reason, that qi's is a true distribution. So how I judge what is her average degree of surprise? It's a log of q taken with a true, I know the true probability. So this is how I judge her degree of surprise, right? So that's mine and that's her. Which one must be larger? Of course, hers. Because if my surprise was larger, I would choose the right distribution, right, by definition. So what I'm saying is that now, if you take this and compare it with this must be, I mean, less or equal than this. So the relative entropy, which is P log P over Q, must be positive. Okay? So this is something which, first of all, shows you that, and just a second, I'll at least 3 minutes, no questions, I'll just finish saying, well, I don't want to interrupt this. Well, first of all, this is the tool, if you look at information theory, particularly in quantum, most of the things that you prove based on the fact, a very simple fact, that relative entropy or all mutual information are non-negative. Now, how they are related, relative entropy and mutual information? Well, if you have two quantities, let's say x and y, right? So they have their joint distribution. That's a true distribution. But you make a hypothesis that their distribution is factorized, namely that they are independent. What is the relative entropy between this and this distribution? It's P log P sum over all x and y. It's a mutual information between x and y. Okay? So what we learned today, I'm now kind of summing up. We learned two new things. Conditional probability, which is another very important thing, we learned at the end of last lecture. Today we learned how to, out of conditional probability, to make mutual information. And then we realize that the mutual information is a particular case of even more general quantity, which is relative entropy. So mutual information is a particular case of relative entropy where your hypothetical distribution is a product. Okay? But relative entropy is even more general fact out of it. And the last thing which I ask you as you go for the break, if now I look at my sequence at the very beginning, you remember, and counted QIs, okay? And then using these QIs, I estimated entropy, which was of Q, and say that the probability of this sequence is actually exponent minus n s of y. Is it higher or lower than the true probability? That if I wait long enough, some q's would be a little bit changed into true p's. Do I underestimate or overestimate doing this microcanonical, this is a microcanonical estimate, right? All typical strings are equally probable. But there are also atypical strings. Intuitively, this formula gives you overestimate or underestimate. What's your feeling? Overestimate. The true probability is lower. Now, this is the right answer. Why? Because relative entropy is positive and you can prove using relative entropy. But intuitively, is it because you assume that this sequence is typical, so you only get your probability based on the number of typical sequences. But there are typical sequences too, a little bit of it. You're a little bit wrong. But your ensemble is actually larger, so your probability is smaller. So your asymptotic equipartition gives you overestimate. And you can look into the book for all proofs. Questions? Yes. Take a mic. Yes.
Can you explain again why physically the Kullback-Leibler has to be positive? You gave a physical explanation just now.
Physical explanation is as follows. So that my degree of surprise when I know probability pi is p log p. Now I see you, and you believe that your probability distribution is q, but I know that it's p. So I judge your degree of surprise. This your degree of surprise when you get event number I, and that an average over I, right? Taken with the true probability pi's. So I say that your degree of surprise must be larger than my degree of surprise, because I know true distribution, right? So I'm less surprised by the data. If you make a wrong hypothesis, you're very surprised, right? So, and this is a very nice way. And I mean, I taught information theory for 10 years until Anton taught me this nice way of looking into things. And this is why he always thinks about entropies as a degree of surprise. And I always think, well, now I'm also learned to think his way, but I more think about uncertainty, which is connected, but it's again, emotionally it's different. Questions? Yes. Take a mic.
So yes, you said that mutual information is a universal powerful tool, but could you please give a few examples as to what kinds of facts can be deduced by using it as a metric?
Look, it's a universal measure of correlations. Okay, like an example what I've given you. We have neurons which have these channels reacting on such electric impulses. Okay, just neurons from the brain. Okay, and then we have this patient being responsive or non-responsive to a lithium treatment for this disease. They are very different things, right? So I have like 4 data, like, you know, potassium, kalium, all these kind of measurements. And here I have this one. I want to know what are their correlation numbers. Because now I want to give doctors a tool. I say, okay, if this number is larger than this, don't use it. Or if this number is smaller than this, then use it, okay? That's it. So you need, and then you try to understand how you characterize correlation between two things. They both are random quantities and very non-Gaussian statistics. That's the way to do it, okay? It's only for Gaussians that it's easy. You take A times B and say, okay, that's the degree of correlation. If it's A times B is not equal to A average times B average, then they are correlated. But for non-Gaussian, it tells you very little. But this is the most universal degree of correlation. Okay?
Thank you.
Yes, take mic.
Can you please explain why mutual information is a subset of relative entropy?
Because mutual information is when you, this is, what is relative entropy? P log PQ. Mutual information is when you Q is just this particular case that you are now making hypotheses about two quantities and you assume that they are independent. So that's your mutual information. If you put here Q, that would be relative entropy. Okay? Okay, we earn the break.
I think there's a photo session, right? So I think before people have coffee, we have a photo session. So where is it? Just outside on the lawn. So please.
We take a photo now.
Photo,
okay,
yeah.
good.